we can provide a selection of items from all that search for it, right? Because you had, okay, I can hear myself suddenly. Because what you had was search engines and information retrieval where you had to give a query. Out here, what the idea was that let's try and learn from implicit information that we can gather as to what it is that people are really interested in. So why search if you can filter? Now, the basic idea being that, especially now with mobile phones, your real estate that you have for consuming items is very small. You have a very large number of items. How do you actually provide to the user from this very large set of items information that he is interested in, or her, she is interested in, I should say. And typically there are two ways in which recommender systems are developed. One is content-based filtering, where essentially as you consume something, the system is watching you, as all of digital media is doing today, and is giving you similar items, right? So it's very, very focused, and if you decide to read something in a newspaper that is about cricket, then the assumption is that that's all you care about in the world, right? And you start getting more and more cricket stuff. And so this is a problem, right? And the problem was solved using collaborative filtering. The idea with collaborative filtering is that in addition to having the items, you also have a pool of people that have consumed prior to you. And so what you try and do is find others that have had similar consumption patterns in the past, and you use what they have consumed and what the active user hasn't consumed and give them that content, right? And of course, the problem with collaborative filtering is that if you have a new item, you don't know how to recommend it because nobody's consumed it up until now. And so typically what we do when we build recommender systems is we build hybrid models that use some aspects of content and some aspects of collaborative filtering as well. Now, the simplest way of thinking of recommender systems is that it's a rating prediction problem. And I'm glad that the speaker before me was talking about regression, because you can actually look at it as a regression problem. You have triples that are given to you. You've got a user, an item, and a rating that they've given. It's a very sparse data set because you typically have hundreds of thousands of items. But nonetheless, what you're trying to do is, as we do in machine learning, is learn a function that, given a pair of user and item, can predict what is the rating going to be. And if the rating looks good, then you would recommend it, right? And so you could use a cost function, and I apologize for the Greek symbols here, but essentially you use something like mean squared error to figure out whether your predictions are close to what has been observed, right? Now, we know we can use linear regression for that. So what we do is we've got our data that looks something like this. We can do one-hot encoding, which gives us a horrible looking, very sparse matrix, where every column is either representing a user or an item, and the rating is our output variable that we are trying to predict, right? And so that's the linear regression model out there. You have n plus m plus 1 parameters. Now, the problem with this is the fact that when a user rates, they don't rate in isolation, right? They have certain preferences. In this case, cinematography, special effects are important to them. And based on that, they're giving ratings to different movies, right? And that's completely missing from this linear regression model here. If you think about what's happening here, you can interpret this as being a rating given by a user is the sum of the average rating given by any user to any item, plus a bias associated with the user. So, if you are a lenient rater, you'll have a positive bias, right? And similarly, an item bias also, right? So every item, if it's Spider-Man, of course, everybody loves Spider-Man, even those who don't, because there's pressure on them to suggest that they do, right? So no matter what, you're going to give it a high rating. So, that doesn't sound right. Where's the preferences in that? So the idea here is to build algorithms that can bring the individual preferences to bear as well, and that's what I'm going to talk about in the rest of the lecture. So typical data looks like this. If Chan here is our friend that we want to make recommendations for the active user, we know that they haven't watched Inception right now. We want to figure out, do they like Inception or not? And the easiest way, and this was the early algorithms that were developed, by the group in Minnesota called Group Lens. They suggested that we can think of a user, this row in the matrix, as a vector in m-dimensional space, where m is the number of items. And now, using simple vector algebra, you can calculate similarity between users and find the most similar users. Take the average rating that they have given to items that have not been rated by Chan, and you make that prediction, right? Now, the problem, of course, is that we have a lot of implicit information that's missing. For example, we've just changed the context of this stick man here, now has children. His preferences have changed. The data we still have are only the triples, so we don't know where the context is, what the context was when they rated it, right? So there is hidden variables in here. What are the hidden variables? They're the preferences and the context, for example, right, in this case. So there has been some work, and rather unsuccessful work, I would think, up until now, in trying to extend recommender systems to say, well, it's actually a function that says a user and an item within a context would have a rating, right? So they are called contextual recommender systems. Now, the view I've always taken on this is that these are all latent variables. And so latent variable models are what you need to use in recommender systems. And we'll look at some of those very soon. So this is what is called user-based collaborative filtering. Using that vector algebra I was talking about, you find similar users. Once you found the similar users, you calculate their similarity, typically with a variation on cosine similarity. And then you take a weighted average of their ratings, and that's your predicted rating. Now, an alternative way of looking at this is to say, if I have to predict this rating here, what have I done up until now? This is my active user. I've found users that are similar to them and taken the average of the ratings that have been given here, right? So only the similar users to the active user that has rated this particular item can participate in that prediction, right? Instead, what I can say is, well, if I want to give a rating to this item, instead of going user-based collaborative filtering, I can go item-based collaborative filtering instead, where I think of the item as being now an n-dimensional vector based on the ratings given by all the other users to that item. And I can then find similar items instead that have been rated by this user and take the average, the weighted average of the ratings for those items by the active user itself, right? So it's just a different way of looking at it, where rather than looking for similar users, we are looking at similar items. Now, which are the items that can participate in making these predictions? They are items that have already been rated by the active user, okay? Now, the problems with this approach, first of all, cold start. If you don't have any users or items, you're in trouble. You don't have any data, so you can't make any recommendations. So if you're a startup, you've got a problem. Even if you have users and items that have been rated, and you're a retailer, what do retailers depend on? New items coming along, right? Or a news casting site, a news website. So what you're going to do there is, you're going to have some way in recommending breaking news. Otherwise, you can't recommend breaking news, right? So that's the cold start problem that needs solved, and we'll look at some ways in which that can be solved, especially in the area of news. The other thing that you also have to recognize is that it's not just about one or two users rating an item. You have to have a certain momentum around consumption of items before they can be recommended. And so one way in which you can measure how good your recommender system is the item latency. How quickly after being introduced as an item is the item being recommended? Okay, so that's just a metric that you could use. You have other issues in terms of sparsity of the data. So if we are looking at two users and trying to compare them, well, out of the 100,000 items, typically a user will have consumed 100. And so the chances of an overlap is slim, right? And so they may have the same preferences, but they, I might belong to the Tendulkar era, and therefore I only know about Tendulkar as the cricketer and all the guys that went with them, and therefore have read only articles about that. Another person who has preference for cricket may be more of a Kohli fan, right? So there is some implicit similarity that is getting missed by the fact that we are looking at just the stories here that we are trying to recommend. And then, like I said, everybody loves Spider-Man. And so if I give a high rating to a Spider-Man movie and you also do that, it doesn't mean that our preferences are the same, right? However, if they're very special, eclectic movies that both of us like, that actually gives us more information, right? So the information bearing nature is a very, very important thing. So one of the key innovations that happened in collaborative filtering, probably now, and I'm losing sight of the number of years, but probably around 15 years ago, was matrix factorization. So what you're doing here is you're saying that, look, we've talked about the fact that this is your rating matrix. You have a few users, you have items, and you have a very sparse matrix here. But the user Tim, for example, had certain preferences. So can we somehow magically construct a preference matrix for a user, where H1 and H2 are two hidden preferences? Now, H1 and H2, I'm giving as an example that there are two latent variables. There could be K or N, whatever you want to call it, a large number of latent variables that would be required to define the interests of Tim. And similarly, every item, if we could define the item in the same latent space, right, where we are saying, if this is cinematography and this is special effects, then item 1 has, as an item, the ability to satisfy somebody who is interested in cinematography to a certain level. And similarly, somebody who's interested in special effects. The problem is we don't have these numbers. So these are our unknowns, and in machine learning vocabulary, we call them parameters. So this is what we want to learn, right? And the way we learn them is to recognize, firstly, that if we wanted to know what is this value here, then we take Tim's vector, and if we multiply it with item 2's vector, we do a dot product of the two, what we should get is a number close to 2, right? So we are doing factorization. We were taught that if you have the number 6, you can factorize it by 2 multiplied by 3. What we are doing here is we are factorizing a whole matrix, right? And so to get this column here, for example, I can take each of the user vectors and multiply them with the item 2 vector alone. And that will give me all of these ratings here. Now what this does, of course, is interesting, and I'll come back to that. But if you imagine that magically we have been able to put these numbers in here, so what we are saying is Tim is interested in H1 and H2 to a great extent, and that's why it has a high value associated with them. Whereas item 1 does not satisfy people that have an interest in H2, right? So these have been learned somehow. I will talk about how those get learned. Now when we multiply each of these vectors with all of the vectors down here, we get a reconstruction of this matrix. And this matrix is not sparse anymore. So almost by magic, we've got numbers where we had no numbers earlier, right? And these are our predictions, in fact. So if we look at this cell here, there was no value there, so we didn't know how Paul would rate item 4. We now have a predicted value of 4.29. And that's a fairly high rating, so we can actually make that into a recommendation. So how do we learn these parameters? Well, it all falls down to doing, oops, I see that this T should actually be up here, so that's Q transpose. But essentially what we are saying is we took the rating matrix, we assumed that the rating matrix can be constructed through multiplication of two matrices, P and Q. P is the representation of users with K interests, so it's a K-dimensional vector. Q, on the other hand, is an interest satisfaction of every item along the same K dimensions. And we have a cost function, which is our rating that is observed minus the predicted rating when we multiply the two vectors. And so now we can do what we always do, which is a search, a heuristic search, right? We'll look at what algorithm we'd use for it. But this is a typical machine learning problem that we are solving here. It's still a rating prediction problem because we're using mean squared error here as our cost function. Now, on an aside, what we know is that any matrix can be thought of as an adjacency matrix or a graph representation. So what we are saying is that the same user item matrix is actually a graph that consists of user nodes and item nodes. An edge exists if user 1 has consumed a particular item, and we can weight it with a number 4 in it, right? And so now what we can think of recommender systems as being is a graph completion problem, where we are trying to see whether missing edges should exist within the graph, right? And there are multiple ways in which this can be done. If you look at Pinterest, some of you may have heard of Pinterest. Their recommender system called Pixie is based on doing a random walk on this graph, right? Where if I have to make recommendations for user 1, I start walking from here. How do I walk? I can follow edges. User 1 could lead to either item 1, item 3, or item 6. We can calculate a probability by dividing the weights on these edges by the sum of the weights, right? And so if you have, for example, user 3 that showed a greater preference for I1, there'd be a higher probability of you walking to I1 than it would be to I6, for example. And you continue this random walk. And what you're really doing is estimating the probability of getting to a particular node, right? And the higher the probability of getting to a particular node, the better that is as a recommendation, okay? But the important thing to recognize is that actually this is no different from what we were looking at earlier. That matrix that we did a decomposition of was really a representation of a graph. And all we are doing there is we are saying, if we started with a graph, can we associate each node with a vector representation? Right? Because after the matrix factorization, what we are really saying, every user is a d-dimensional vector, every item is also a d-dimensional vector, right? And we can then utilize that in some of the more complex models that we will come to. Another approach is something some of you may have heard of, is graph CNNs, right? Convolutional neural networks. If you think of a convolutional neural network, typically you think of image analysis. So image analysis, what are you dealing with? A black and white image is a matrix of numbers, not that different to a user item matrix, right? And we've already said it's a graph. It's a kind of an interesting graph in that every pixel is now a node and is connected to neighboring pixels, right? And the number of neighboring pixels is uniform in an image. Out here, it's not uniform. So when we look at graph convolution neural networks, we actually look at message passing as the approach. Now, we don't have enough time to really get into the depth of graph convolutional networks. I'm happy to kind of talk of it offline with you if you want to. But essentially, all of these methods, what they're trying to do is say, given a graph, can we convert that graph into a representation where every node is now a d-dimensional vector, right? So all of these methods are approaching the same objective. Now, if we think about the rating that a user is giving to a movie, we can break it down. We talked about the fact that a rating, you can think of it as an average rating given by any user to any item, plus you add an item bias, plus a user bias, and then there is some play of preference. And I said when we were looking at it from a linear regression perspective, I was saying that this is the piece that's missing in linear regression, right? So if we take an example of Star Wars and a rating that you're going to give, everybody loves Star Wars. At least you can't say you don't. So it's going to be a positive bias. So typically you would expect a rating given to Star Wars to be higher than the average rating given by any user to any movie. Derek, our user in this case, is a harsh rater. He's like me when it came to my students' impression of me at least, that I'm a hard marker, right? So he gives hard ratings. And this is an important thing to remember when you're building recommender systems. You're collecting, crowdsourcing ratings. Everybody has a different rating. I may be such a horrible person that I say no movie made to date, because I haven't made a movie yet, is good enough to get a 5, right? So my ratings are going to be 4 and below. And that's what Derek is like. And so his bias is a negative number. So the fact that we are predicting Derek's rating is reducing now our rating of Star Wars. And then there is this piece. Now, given that Derek likes science fiction movies, we are expecting his rating to be higher than other movies that are not science fiction. And we know how we can now calculate this by matrix factorization, right? And so what we can do is, I'm going to skip this. What we're going to do is, we are going to use as our cost function this horrible looking thing, where this is the rating that has been observed, and this here is actually our predicted rating, where we have identified the average rating. Average rating we can just calculate by truly taking the average of all ratings in our data. We have enough data there, right? Item bias, user bias, less so, because we don't have a lot of data. If we have a new user, we've got no ratings. If we have a new user that has rated 1 or 2 items, that's not enough to really calculate any statistic, right? And so we treat these as parameters as well. And of course, our P and Q vectors are all parameters, right? So the sum of all these 4 things is our predicted rating, and we're still calculating the squared difference between the 2 of them. And what are we now doing? We're using gradient descent. So we are doing an iterative optimization where we are updating all of our parameters, the BIs, the BUs, the PUs, and the QIs, and learning them. So what we are really doing is we are saying, remember our one-hot encoding? We have now added an interaction columns in here also. And it seems kind of bizarre, but what we are saying here is that this 3-dimensional representation, we have now got into a m plus n plus m times n representation, where we are saying the rating out there is given by user 1. Item 1 is involved in that rating, and the rating is dependent on the interaction between user 1 and item 1. And so we end up with a linear regression model. But look at what has happened here. What is interesting is the parameters. The parameters that we have, the beta i's in linear regression, we have now said, well, some of them are still beta i's, but now we have a product of 2 parameters instead, the pi's and the qj's, right? And so this is not a linear model anymore, because when we talk about linear regression, we are saying not linear in terms of the input variables, we are saying linear in terms of the parameters, right? And so we have a problem. This cost function is not convex anymore. So you're going to have lots of local minima in there, right? So it becomes a more difficult optimization problem, but you've got a better representation. So, so matrix factorization is really only doing something exciting with linear regression. Now, what we typically use here is stochastic gradient descent, because that is known empirically to be able to navigate around local minima. An alternative to that is the alternating least squares. And what that says is, for now, if we look at this, what was the problem? Why was this not convex anymore, the cost function, when we subtract this from the observed rating and square it? It's because of this product, right? So the alternating least square says, let me fix PIs and treat it as a convex cost function and only change my beta 0, beta I, gamma j's and my qj's. After a few iterations, let me fix q and only change the PIs, right? And that's what alternating least squares does. So it kind of almost factorizes the search problem that we have. Now, this is where things start getting interesting. So you may be too young to know this, but there was once upon a time a Netflix prize that was run back in 2006. And Netflix put behind research in recommender systems by 3 years, because all the researchers decided, forget about research, I'm going to win the Netflix prize. It was $1 million on offer. And the data that they gave was 480,000 users. I'm sure they have 10 times that now. And 17,000 movies, 100 million ratings. And the task given was to improve the mean absolute error in rating prediction compared to their existing recommender by 10%. Okay? And of course, the whole research community gave up on everything else and worked on this for 3 years and actually cracked it. So they did win the award, a bunch of researchers that got together. But that recommender system never made it to production because it was just too expensive. Okay? So we've got to kind of balance these two things. Now, one of the things that came out of it was an interesting piece, which was, it said that, well, even if we do matrix factorization, the number of parameters is 480,000 plus 17,000 times k, right? Because you have the user matrix, which is 480,000 rows by k parameters. And you have the item matrix, which is 17,770 by k parameters. So, and users are going to continue to grow. So what they said was, why don't we think of the fact or recognize the fact that a user is really some kind of an aggregation of the items that have been consumed by them. Okay, and so what you're saying is that what if instead of having a vector for a user and a vector for an item, why don't we create two vectors for items instead? One, which is the k-dimensional representation of an item in terms of its ability to satisfy people with the different preferences. The other vector is a representation of an item in terms of its contribution to representing a user that has consumed it. Okay, so what we are doing now is we are saying that the rating matrix, the factorization we are doing is now a factorization that consists of three matrices, A, P, and Q. P and Q are now M by K matrices, both item matrices. A is an N by M matrix, but it has a constant. This constant that Patrick came up with, right? Where we're basically saying that for every item that has been consumed by a user, I'm multiplying it by a constant and adding it up. And that's my user profile. Okay? So that's what they did here, and they reduced the number of parameters, and it didn't really impact the accuracy of the model very much. And if you think about this, this is not that different to when we think about word2vec. For those of you who've looked into word2vec, you must know that for every word, we don't get one vector, we get two. And then we take the average of the two, right? So in a similar way, what we are doing here is we are creating two vectors that represent the different aspects of the item. One in terms of its contribution to representing users that consume it, and one in terms of its ability to satisfy the user themselves. So one of the first recommenders we built was a news recommender. I mean, in this avatar, right? Back in the 1990s, we built a recommender for movies because that was the thing everybody was doing in Northern Ireland. But this was our first recommender in India. It was a news recommender system. And the problem here that we faced was that the user item matrix, we have a problem that we have new news stories coming along all the time. So what we did instead there was we took the philosophy of collaborative filtering. So for every news story, we said, what if we can represent them by a set of features? The features could simply be a vectorization of text, right? Or it could be the named entities that we extract from them. And we calculate the user profile similar to what Patrick had talked about to say, well, if I've consumed these stories, then the aggregation of those three news stories is my user profile. What have I ended up doing? I've started to now represent a user in the same space as the items that they're consuming. So I can literally calculate the Euclidean distance between them, and I can recommend news stories that are similar. Or I could take the dot product. But I'm not satisfied with that because content-based filtering has a couple of problems. The biggest problem being that it has a narrow focus. So what I do here is I now take my neighbors from the other users that have consumed stories as well, and I aggregate their vectors with this one. Now, if I have vectorized my news stories using a topic model, for example, I may have only consumed cricket out here. But what's happened here is that other people who consume cricket may have also consumed world politics, right? And so in my topic signature that I get here, I'm now getting world politics also. And so now I have a representation which is an enriched user profile, and I can match it against the other stories that I have not consumed right now and get recommendations for myself. We use the same thing so I run a foundation as well called Subudh Foundation, where we teach AI and ML for free. I hope there are no edtech folks here. So we built a platform during Corona's destruction of mankind. And on that platform, what we did was we created a collaborative learning space where people can ask questions similar to what you do in Quora, right? But people who are consuming our content. And so we wanted to route questions based on which person is most likely to be able to answer the question of a peer. And so again, we use the same kind of ideas around here and built profiles of individuals based on their proficiency across the platform. Now, while everybody thought that the recommender system issue is resolved, Yahoo Research released a research paper that destroyed the souls of most researchers. And what they did was they said that let's do a research project around how do ratings get collected. So they did an A/B test where to one group, they gave them access to Yahoo Music and said, here is a random set of music out of the Yahoo set, and tell us whether you like it or not. And when they gave the ratings, you can see that a lot of the music was actually all ones, not liked, right? To the second group, what they did was they said, you've got access, search for whatever music you want and rate it. The distribution was very different. You had 5s and 4s appearing as a large part of the ratings, right? And why they did this was they wanted to highlight one very important assumption in machine learning. And that assumption in machine learning is that the probability distribution remains stationary. Right? If your probability distribution shifts from under your feet, you're going to fall, right? Your predictions are going to be all wrong. And so what they said was that this is how ratings are currently consumed. There is a preference bias. A user may read the metadata about a movie on Netflix and say, nah, this doesn't sound interesting. If they don't consume the movie, they're not going to rate it, for example, right? So whenever we ask for ratings, they're always for items that have been consumed by the user that has a filter on it, which makes it more likely to be an item that is liked. When we are predicting, though, all that space that was in the matrix where we don't have ratings, the majority of items are ones that we won't like, is what this distribution shows us. So we are building a model on this distribution, predicting on this one. So they said rating prediction is a bad way to go, right? And all the research that had been done for the Netflix prize and everything was all around rating predictions. So what they suggested was you should look at it as a subset selection problem. So you have a large number of items, you want to select those items that are most likely to be of interest. Now you could say that actually, how's that different from rating prediction, right? Because I'm predicting ratings and I'm ranking based on ratings and I'm picking the top N. The problem is the fact that that whole rating prediction is inaccurate and incorrect, is what the Yahoo research told us, right? And so this led to a very interesting piece. So firstly, if you're looking at top-end recommendation, you're not really focused on ratings anymore. You need different metrics to make your evaluation. So what you want to see here, for example, is precision and recall, right? Are items that I've hidden away from the algorithm that did the learning of the model, the items that have been rated by the active user, how high are they in the ranked list that was predicted by the item? ARHR does that calculation. Precision and recall look at the top K and see whether it appears or doesn't appear in there. And then what they did was what I thought was a master stroke, right? They said, we've done so much work on matrix factorization, let's not give up on it. So what they did was they said that we will set all the missing ratings, we'll give it a small rating, Rm. Right? So we take this sparse matrix and we give all the missing values a small value. A small value is basically saying it's a low rating, close to 1, right? So why are we doing this? Because Yahoo research told us most of the things that have not been watched are not of interest to the user, right? The next thing they did was they also set a weight, which was used in the cost function. And here they said that the weight is 1 if the rating has been observed, and it is a small value Wm if it was a missing rating, and Wm is going to be a value less than 1. Right? And in the cost function, we are still doing the matrix factorization and adding it to this Rm value that was added in there and doing the mean squared error. But I am telling the cost function that if I make a mistake for a rating that is not existing in the data I was given, ignore that mistake, compared to if I am off on a rating that has been provided by the user. And this led to the idea of negative sampling, basically, right? So in some of the other algorithms that we will get to, you'll see the fact that in addition to taking the observed ratings for users and items, they actually took user and item pairs and gave, chose a user item pair that was not rated and said that is a negative sample. That's an item that's not going to be liked by the user, right? So that was one of the biggest advantages of this. And now given this cost function, we were able to do matrix factorization and set Wm and Rm that are now hyperparameters of this algorithm to maximize recall or ARHR, those metrics that we just saw, right? So while we are using ratings here, we are not actually fixated on those ratings. So this is all good. And then what happened was a customer of ours said that we want you to build an app that you open your fridge or your larder in your kitchen and take photographs of it, and you should recommend what I can cook. So we said, okay. So, we used vision algorithms to segment these images, identify different pieces. We also used some text analysis to read labels and figure out what there is. And now we have features for the items as well, right? So now we don't just have recipes that have been consumed and given a high rating by users. We have features additionally. We also have user information that says, I don't like this, or I'm allergic to this, right? So that was another dimension. So now what we are saying is, it's not just a triple. It's a user, item, rating, and then user attributes and item attributes that also need to be incorporated. And this matrix factorization doesn't really work very well in that sense. But recognizing the fact that really what we are doing is linear regression in the end of the day, we have to recognize that a recommender system is a function that maps a user vector and an item vector onto a rating or onto a propensity score. So this came up in the last session also, where somebody was asking this question about propensity. Actually, that is a completely valid thing to do, is to say how likely is somebody to click on this or to buy this, okay? So actually the state of the art recommender systems actually do that. We're just very fixated on matrix factorization. When you think about it, it actually works out quite nicely, and hopefully we'll get to there in time. The other customer of ours in the fashion industry said, actually, I have customer registration data also. I also have purchasing behavior, and I don't have any ratings, but I do have product features, and I also know if somebody viewed an item or didn't view an item. So how do we include this stuff? So one of the things we did, as you can see from my gray beard, we are very fixated to kind of find, do feature engineering, right? Even though deep learning folks say you don't need to do that anymore. So, but And they're wrong, of course, right? So what we did was we looked at sales data as a time series, and we started to kind of say, well, one of the interesting things here are the patterns. So this item here, it lived for a short period of time and then disappeared. So anybody who actually buys this item at this point, we thought is a fashionista. So that's somebody who figures out when it's released that this is going to be a hit, I want to buy it. These are, of course, the wannabes or followers that buy it after the event has already taken place. And these are my favorites. The ones that say, after it's sold, it probably goes on sale again, I'll buy it then. Right? So they are the price-sensitive folks. And similarly, you have eclectic users that are the ones that buy things that aren't very popular. Not too many people buy it. It might be ephemeral in the sense that it lasts for a long period, not over a very long period of time. But people like it, and therefore they have eclectic taste. And then you have staples that sell throughout the year or seasonal products as well. So we did some kind of feature extraction there. And we also used image analysis for creating tags for these images, right? So currently humans were doing the kind of tags, and I didn't know there were so many dimensions to clothing until I worked on this project, and that's part of the joy of being a data scientist, right? So there's neckline and style and fit and sleeve length and all sorts of things. So we used image analysis to figure all of these features out. We had to deal with the fact that we had a very skewed distribution for these tags. Nonetheless, we used all the standard machine learning stuff that we do. So when we get excited about recommender systems and say it's a different beast that we're dealing with, the truth of the matter is it's not, right? In the end of the day, it's either a regression problem or a classification problem, right? So don't fool yourselves. Okay. So then, of course, not to be left behind, the deep learning folks said, no, we can do this better. And they came up with the fact, and this is actually a very interesting fact. If we think about what we were doing in the news recommendation, right? We were taking vectors of news and we were aggregating them, taking the average of them. And then when we wanted to compare a news story with the user, we took the dot product. And we said this story is close to the user, so we'll predict it. There's no learning there. We don't learn what it means to be a news story that is similar to a user or is going to be, enjoyed by a user. And so the first thing that was done here in neural collaborative filtering, where they said was the input is still the one-hot encoding of an item and a user. We will learn the user's latent vector. So the matrix factorization piece is happening here. It's the weights, right? That's taking this m-dimensional vector of users, converting it to k dimensions. It's taking the n-dimensional vector of items and converting it to k dimensions again, right? And so the P and Q matrix are actually these weights. Does that make sense? Yeah, so you can actually do a matrix factorization and seed an embedding layer here in the neural network, right? And use those embeddings to create the initial weights. And then what they said is rather than a dot product, what I'm going to do is I'm going to shove these two into a multi-layered perceptron. So I'll concatenate these two vectors, push it into a multi-layered perceptron, make it as complex as I can, because I like doing that. And I'll never try it with just one layer, of course, right? Because my boss will not be impressed. And finally, the one restriction I have here is I'm going to use an activation function, which is sigmoid. Why? Because I'm only trying to predict here whether the item will be consumed or not. So what are we building here? We're building a propensity model, okay? But here is where the interesting thing comes. We have only positive examples and we're building a classifier. So to get the negative examples, what we're doing is taking a random sample of unobserved items and saying those are probably wrong. No, not probably wrong, they are probably ones that I will not enjoy, okay? And if you actually look deep into even Word2Vec, for example, they use negative sampling there also, right? And so we're not doing anything too fancy out here. So this looks all good. Then, of course, because it's deep learning, we want to make it even more complex. So what they said was, This is cool, it uses a neural network, it must do better than matrix factorization. They compared it and it didn't. Okay, so they said, no, so there's something wrong here. So what do we do here? We'll cheat. So what we'll do here is we'll put matrix factorization into the neural network. Okay, so the neural networks are great things, right? Because they're basically computation graphs. You can do whatever you want inside them. So what they did was they took the user and item one hot encoding vector, and rather than projecting it into one k-dimensional space, they did it twice. Right? All you're doing is you're multiplying it by an n by k matrix. So now you can have two different n by k matrices, you get two different representations. Right? So you have two different representations out here coming from the user, two different representations coming from the item. What they do here is an element-wise product of the two vectors. So they take one of the item vectors, one of the user vectors, and do a dot, not a dot product, but an element-wise multiplication. And they get a k-dimensional vector here. Out there, they do what was happening previously, the one that didn't work, right? So they're taking these two, concatenating it and passing it through a multi-layered perceptron. And now the output from here, remember, this is not a dot product, so it's not a single number. It's actually a vector. They're taking the concatenation of that, passing it through one layer, putting an activation function of sigmoid, and getting a probability. Right? So they've now incorporated it and said you can learn your weights yourself to the neural network. And in the worst case scenario, if all those weights become 0 out here, you fall back to matrix factorization. Okay? But again, the difference here, the additional layer here, is that we are now saying matrix factorization, but we are not using the dot product anymore. We are actually learning the similarity function in that last layer at the top. Okay. And so then they generalized, and this is where it starts to get interesting. Because the generalization they did was to say, a user, it doesn't matter where I'm getting the features from. They could be features like, I have a candidate that I want to match to a JD, right? I've got an embedding of his CV because that's the easiest thing to do, right? Just throw all the text in and say, let me get my word2vec or BERT vectorized representation of text. But I've also got some structured information. I know his job title, right? I know where he studied and so on. And I can create separate one-hot encodings for each of those fields, and I can concatenate them. So an aspect of the recommender system is to do representation learning. So for a user or for an item, right? So what we are saying is we need to create a vector representation for a user or an item, and we can do all our feature engineering we want to do now and put that in here. Once we have that, we will create an embedding from it, right? A lower dimensional representation. We will learn how to aggregate those two together and map them onto a matching score or a propensity score. Right? And so initially what they said was, well, rather than using a one-hot encoding, why don't I actually represent the user as the row in the user item matrix? So now it's not a one-hot encoding where I'm saying this is user 37. I'm saying this is user 37 that has rated all of these items, right? And putting that in. And similarly for the item, we take the column and put that into the neural network. And what's happening here is we are learning the representation P and Q. And we are doing a dot product, which is the simplest version of a neural-based representation learning. And of course, we can add to that, once we've learned the user representation, we can add a second piece that actually does the matching algorithm rather than the dot product as well. Okay, 3 minutes before I have to stop to take questions. Oh. It's not easy talking that fast for so long. Okay, so there's another algorithm. We won't spend time on this because we don't have that much time, but essentially it follows the same idea, and hopefully you can see the continuum that we have in recommender systems, DeepCF. This is an important piece, so I shall stop here. Now, one of the other pieces of research was to say, well, what if I take all my features and use an autoencoder instead, right? So all of you know an autoencoder. It's basically a non-linear dimensionality reduction, right? So it's principal component analysis on drugs. So what you're doing is you're putting your input vector, which is the input vector, which is the row for the user, all the ratings of all the items, and you're trying to reconstruct it with a lower dimensional representation. Now, what they did here, though, was to change the learning algorithm to say, I'm not really that bothered with reconstructing unobserved values, right? So every user is a partial representation of the user's preferences. So items that have not been rated still have to go as input, but I don't care what their reconstruction is. I only care about the reconstruction of ratings that I have seen. Ratings, or it could even be a binary vector saying, you know, he consumed and did not consume, right? And so you get this representation. And so given this, what we built was this, which is the recommender system for matching a company's desire for an employee and the various candidates that are out there, right? So knowing their industry of the company that they're working on, the revenue of that company, something else that I can't read because there are too many dots here. You know, so we took all the features that we had and we squashed them into this vector representation using autoencoders. We then concatenated those representations and passed them through multi-layered perceptrons that actually gave us a match between what is being looked for and what is on sale. And last but not the least, and this is what makes neural networks really interesting, is the fact that you can play with how you construct the layers, right? And this cross and deep embedding neural network, what it does is very interesting on the left-hand side. So the input layer here, you can see is a concatenation of vectors. Just as I said, if you have multiple features, categorical features, you do a one-hot encoding of them and you concatenate all of those, right? Now what you're doing is, on the left side, this input vector is being multiplied by the output in every layer in here, okay? So what you're constructing in here, and again, we don't have enough time to go through this, but what you're constructing in there is essentially a n degree polynomial of the input vectors, right? But input features, but with many less parameters than what you would require if you just use standard polynomial regression, right? And so with much fewer parameters, you can actually get the same effect and learn rather complex functions. Now, my understanding is it hasn't really proven itself in the real world, but I just thought that this is very interesting and I thought I'd throw it in here. That, you know, thinking about the architecture and what impact it has on the underlying function that you're learning is something that most people don't do these days. So it's a good idea, is my last message to you. And then finally, sorry, there was one more thing I wanted to talk about. Content sometimes isn't standalone. So we can think of content as being a graph, right? We've got movies here. You've got nodes of actors and directors and all sorts, and they're connected to each other. B2B marketing, right? The items of marketing content don't live on their own. They may be case studies associated with a particular industry. They may be associated with a product. They might be associated with a region, right? And so you have this kind of graph representation of content, okay? And so now what I kind of touched upon, and therefore I will skip the rest of the slides. The idea here is to use graph convolution neural networks to create a vector for every node. And that vector now, the advantage of the vector that's created here is it takes into account the multiple hops within the graph also in coming up with the vector rather than just looking at the content within that item itself, right? And that can then, because you now have an embedding, can be fed into a more complex model like this if you wanted to, okay? So recommender systems is a fascinating space. While I've been saying that it does nothing, so those are called network embeddings, and I won't go into any detail on that. I'll go to this slide here which says, thank you.